Hi, welcome to EC&M Tech Talks. This is a series of how-to videos where we cover everything from, equipment we install out in the field to the codes and standards that govern the installation and maintenance of that equipment. Sometimes we get into how that equipment works and so forth. Anyway, I'm Randy Barnett. I'm your facilitator for today's presentation, and this is brought to you by EC&M Magazine, Electrical Construction and Maintenance Magazine. So if you go to ecmweb.com, if you haven't already, then go to ecmweb.com. On that upper left-hand corner, there's a drop-down menu. Click on that, and the very first item that you're going to see is premium content. So sign up for the premium content, and you will get some lots of good information that has to do in our professional work of electrical installation and maintenance. Then, all righty. Especially on today's topic, there's a good article out there as well on termination. So anyway, let's get going. We're going to talk today. We're going to use the 2023, which is the most current NEC, National Electrical Code. And today we're going to talk specifically about section 110.14. 110.14 is on electrical connections. And there are four important parts to this particular section that we need to pay attention to. Well, I guess even before that, there's some general information that we're going to talk about as well. But things like terminals, terminations, in other words, splicing conductors, temperature limitations. That's kind of interesting. We'll talk about that and see how that applies out in the field. And finally, torque connections. That's one of those things, torque, that maybe we don't pay a lot of attention to. There's some guidelines that we're going to look at that are in the NFPA 70 handbook, or now on Link NFPA or NFPA Link. And so you can access that information. But anyway, let's get started. First of all, just some general information. You know, if I take two dissimilar metals and put them together, there's going to naturally be some corrosion that's going to want to occur between those two different metals. Now, if I take a piece of copper wire and aluminum wire and put them together, I'm going to start to get some corrosion. And if I've got corrosion, I've got resistance. And if I've got resistance, I've got heat. And that heat loss is an I squared R loss, isn't it? So if I double the current flow, I produce 4 times as much heat in a given resistance. But anyway, what happens if I join copper and aluminum together? Then they start to corrode, they start to heat up. I get more corrosion, more heating, more corrosion, more resistance, more heating. Of course, it spirals out of control. I got a call one time from actually a friend who said, "Hey, I smell some burnt insulation in my closet. Could you come over and take a look at it?" Sure, I'll be right over. Okay. And sure enough, there was a junction box in his closet going to a boiler feed pump down into his basement for his hot water heating system. And somebody somehow years ago, whenever, whatever, had used aluminum wire in that junction box to go from copper down to that boiler feed pump. Corrosion had occurred, and all that left, I wish I had it here today, all I had left of that wire nut was a red glob of plastic. Okay? So it happens. It's a real world thing. So we want to make sure that if we're going to put dissimilar metals together, that whatever it is we use, and it says we can use it for dissimilar metals. For instance, on the back of this receptacle, which of course you can't see all that fine black print on the black plastic, huh? But anyway, it tells me Cu for copper, so I can use copper. Then it has Al, but there's a slash through the Al, meaning don't use aluminum. In fact, it also points out in 110.14, if you are using those little holes in there where you just push the number 14 and only number 14 in there to wire up these devices, then that can only be copper wire. We'd never want to try aluminum in these. But anyway, follow the instructions. Always follow manufacturer's instructions, right? So dissimilar metals, if I'm going to put dissimilar metals together, such as copper and aluminum, I can buy wiring devices. I can buy twisted on pressure connectors, wire nuts, right? They'll be listed for both copper and aluminum. So I can certainly use them for that. So that's probably one of the most important things right off. Don't mix your copper and aluminum unless that device or wiring device, whatever it is, says you can do that. Otherwise, you're asking for trouble. You're asking for fire guarantee. Now, by the way, a lot of people, criticize aluminum wire. The AA 8000 series, which came out many years ago, good aluminum wire now. We use a lot of aluminum wire, don't we? Feeders, service applications, larger applications. We see a lot of aluminum wire out there. And when terminated properly, it's great. Now, one of the other things is that it says if I'm going to take a stranded conductor, and then crimp on a lug onto that, I got to be careful. How many strands am I going to put underneath that lug? Everything in our code book is listed for either, really, if I go to chapter 9, table 8 in the code book. So chapter 9, table 8 gives you conductor properties, and it gives you all the dimensions on a given AWG conductor and all of that. And for stranding, it'll list like 1 or 7 or 1 or 19. If it's only one strand, that means they're talking about a solid conductor. So all the dimensions after that are for solid conductors. But if it says 7 or 19, that's the number of strands per that conductor. And that's called B-stranded conductor. So we have B-stranded and C-stranded that are in the code book. And there's another another table in chapter 9:10 that talks about conductor stranding. So here's how that works. If you take a look at chapter 9, table 10 on conductor stranding, what you're going to find is it lists for a given size conductor, it lists the number of strands, either B-stranded or C-stranded. If it's C-stranded conductor, it'll probably list more strands to it. But after that, it doesn't list anything else. And we can buy other types of conductors. For instance, we can buy DLRO, locomotive cable, right? We use that in some industrial applications. What about welding cable? There are a lot of strands in welding cable. And the reason that we want that heavily stranded conductor is because it's flexible, right? And we want that flexibility. But if I'm going to put a lug on that stranded conductor, I want to make sure that that lug, and when I crimp that lug on there, I'm not damaging any of those strands underneath, in the barrel of that lug. So I want to make sure that I'm using the proper lug for those number of strands. So generally, B and C type stranding on any lug we buy is going to be fine for B or C type stranding, which is listed in the code. You might run into some D type stranding, which is more strands, but something like, I'll give you an example here. I looked up in chapter 9, table 8, 4/0. So 4/0 conductor, chapter 9, table 8 says that 4/0 has 19 strands, and then it gives all the dimensions on the individual strands and the overall dimensions for a 4/0 conductor. Locomotive cable size 4/0, so the same size, its conductor stranding is 551 instead of 19. That's a lot more strands. So it's actually 551 strands of 24 gauge conductors. So 551 24 gauge conductors all stranded together in that 4/0 cable. And so that refers to it, and that particular vendor said that's class I stranding, okay? Welding cable, for instance, is class K or M stranding usually. Now, what all this means is that if I go to crimp a lug onto a cable, I'm working with something out of chapter 9, table 8, class B stranding. I buy my lug and I put on there, okay? If it's something more than class B or C stranding, that lug that I'm going to crimp on in that crimping device, it's got to be identified for those number of strands or that particular class of stranding, whether it's K or M or 64 strands or 551, whatever it is. So some way that I know that I'm using the right lug on that particular conductor then. Terminals. It says that my terminals have to be mechanically secure. No kidding, okay? Manufacturers provide us torque specifications in many applications, don't they? And if that manufacturer gives us a torque specification, we got to pay attention to it. So whatever my torque specification is, I don't know. Here is a double pole 40 amp circuit breaker. And let's see what I can read on here. 45 pounds, 45 pound inches. So 45 inch pounds, 5 Newton meters. Alrighty. So I'm going to have to torque these terminal screws on here to 45 inch pounds. Now, another thing, these particular screws I noticed are a little bit different. Right at the beginning of 110.14, it talks about making connections and so forth, and how the different devices that we can use to make connections. And one of the things that it talks about is wire binding screws. This is an example of a wire binding screw. This is a 15 amp circuit breaker. And on this 15 amp circuit breaker, to connect my conductor, I've just got it's a pretty much, standard screw with a head on the screw. And when I screw the screw down, I clamp down, don't I, between two little flat metal clamps with room for the conductor in there. And I clamp it down and tighten it down to whatever the torque requirement is. On the wire binding, and you've used these before, certainly, it's the same thing except different, okay? The screw, there's no flat head on the screw. It's a set screw. And it requires a screwdriver. I looked it up in the U.S. Patent Office anyway, and it said it has to be a screwdriver to be called a wire binding screw. So anyway, it's a set screw that we put in there and we tighten down. And what we want to pay attention to is the number of wires that we can put underneath these terminals. For instance, on this 15 amp circuit breaker, it allows me, if I look on the side of it, it says that I can put two number 14 to number 10 gauge coppers. Okay, so 2 to 14, number 14 up to number 10 gauge coppers, I can put underneath that terminal screw. And there is room for 2 conductors under there. On my double pole circuit breaker, on the 40 amp circuit breaker, it doesn't say anything on the side here about 2 conductors. In fact, it only, it's got a little picture, and it only shows 1 conductor. 8 gauge copper. Then it says, get some other information on other conductor sizes, but only 1 conductor underneath that terminal. And if you were to look at these side by side, when you have a chance to do that out in the field somewhere, whatever, big difference in construction on those terminals, right? And you can see why the 40 amps only allowing 1 wire under there, and the 15 amp is allowing 2 wires under there. So that's also a requirement in 110.14. Tell you another place we've run into trouble on that, though. Take a look. Over here's the panel board we use in a lot of our tech talks, right? And in that panel board, there's a grounding bus bar. That grounding bus bar is pretty easy to use, isn't it? If you're familiar with those, and it's pretty easy to get 2 number 14s under there, and yeah, I can create some more space in there and whatnot. But you know what? Unless that termination device says that I can put more than 1 conductor under it, I can't. And I didn't see anything on that terminal bus bar or on the panel instructions that says I can put more than 1 wire underneath that terminal screw. So be aware of that one. You'll see that violation a lot out in the field, won't you? Not just on bus bars, but on wiring and relays and everything else. Section B then talks about splices. Have to be spliced with a device identified for the use. We use a lot of crimp-on connectors, and we've talked about the stranding configuration as well. But we use a lot of ferrules to crimp splice wires, conductors together. It also talks about using welding, brazing, or soldering, and so forth. We probably don't do much of that anymore. We clamp it on there, don't we, and crimp it, and we've got our splice made up. Once again, got to make sure you're using the right conductors, the right crimping tool, and you're following the manufacturer's instructions for stripping the wire, the insulation off the wire, and for actually crimping that lug on there. Ready? Any chain is only as good as its weakest link, right? Sure it is. I remember back in my maritime days, right, back in the Navy, okay, we would have big, huge anchor chains, big, huge links on that chain. And each one of those links was made of steel, big round steel like that for each link. And I don't know how much that anchor weighed, but it was a big hydraulic winch that would lower that anchor and pull it back up. If one of those links were ever to break, that big, huge ship would just start drifting out to sea. And we can't let that happen. Now, it's a little bit different in wiring, I suppose, and that we don't have to worry about anything drifting out to sea, but we got probably something more important to worry about. Any chain is only as good as its weakest link. If I have a weak link somewhere in this system, I could have a fire, and I don't want a fire. That defeats the whole purpose of the National Electrical Code, Section 90.1, doesn't it? Okay, protecting people and property from the hazards arising from the use of electricity. So let's go to chapter 9, or excuse me, let's go to table 310.16 now. So let's go to chapter 3, table 310.16. Our ampacity table, in other words. If you're using an older edition of the code, it might be table 310.15b16. But in our 2023 code book, it's 310.16. I just call it the ampacity table, and it's on page 187 in my 2023 NEC. So when I take a look at, let's see, I look and I've got either copper or aluminum. And then I have different classifications of insulation and then different gauge sizes. Well, anyway, I look at this, and this is THHN insulation. Copper conductor, I can see the copper on the end of it, right? So it's a copper conductor, and it better be, because this says copper only, right? Or at least no aluminum. And so it's copper 14 AWG THHN. I know already that's going to be rated for 90 degrees C without even looking in the code book. How do I know that? It's THHN. The T tells me it's a thermoplastic insulation. The two H's, HH, tells me that it's suitable for 90 degrees C, which is 194 degrees Fahrenheit. That would be the maximum operating temperature on the insulation. And then the N tells me it has a nylon jacket. So I look in my code book and I go down, and sure enough, there in my 90 degrees C column, I find THHN insulation. And then I look down and I look to the left and I find my different gauge sizes. And we said this was 14 AWG, this black conductor I have connected to the receptacle. So it tells me that that has, number 14, has an ampacity rating of 25 amps. Okay, so 25 amps. And so my next question is, okay, then what is the, so 25 amps, let's talk about that. So under its conditions of use, and ideally, let's say it's 86 degrees Fahrenheit, the code book tells me, and used in a not more than 3 current carrying conductors in my raceway cable, and I just got one conductor here. And I don't know, let's say it's 86 degrees Fahrenheit in this room right now, a little bit warm. Anyway, THHN then, that could safely carry, it tells me 25 amps of current flow without overheating the insulation. In other words, the insulation would not exceed 90 degrees C. So it would be right up at 90 degrees C with 25 amps of current flow through it. Great. That means that terminal screw is going to get up to 90 degrees C, doesn't it? Is it rated for 90 degrees C? I don't know. I look at it. I don't see any rating on the terminal screw, so I don't know. But 110.14 is going to tell me. So I go back to 110.14c on temperature limitations, and it gives me some information to follow. It says if my device is rated for 100 amps or less, or marked 14 gauge through 1 gauge, it's a 60 degrees C terminal. This 15 amp receptacle is certainly less than 100 amps, isn't it? Okay. And 14 is certainly a smaller size than 1 AWG. So this is a 60 amp C terminal, or excuse me, a 60 degree C terminal. So if I put my 25 amps of current flow through this device, I'm going to overheat that terminal, and I could have a fire. I don't want that. So I'm going to have to limit the amount of current that flows through this wire to make sure that I don't overheat that terminal screw. So to do that, I go back to my ampacity table. I go all the way to the left now, and I see the 60-degree C column for copper. In the 60-degree C column, it tells me that I'm going to have to limit the amount of current flow through this wire to 15 amps. Well, that makes sense. I'm going to limit it to 15 amps. It's a 15 amp receptacle, and check to get most likely right with a 15 amp circuit breaker. Think of that though. It should make you feel pretty good. So here I've got a conductor that can safely carry 25 amps of current flow under those conditions of use stated in the table. 25 amps. I'm going to take and put this number 14 wire behind a wall where it's no longer exposed. Nobody can see it. It's going to sit back there for years and years and operate. I hope it doesn't catch on fire. Well, should it? No. I've got a wire that's rated for 25 degrees C, and it's limited because of the device, which is inside of a box, by the way, right? I'm limited to 15 amps of current flow on that. So that's, I always thought of that, well, that's kind of a lot of overkill, isn't it? That's a good thing. Sounds like it to me. Be safer. So anyway, that's my temperature limitations. Now, when it comes to motors, B, C, and D motors, class B, C, and D motors, just look on the nameplate. Those are going to be 75 degree C terminals. 75 degree C terminals, often marked, but 75 degree C terminals, let's see, rated over 100 amps are conductors larger than 1 gauge. So now we break over from that 60 to 75 degrees C. We go to conductors greater than 100 amps or greater than 1 gauge, and they're 75 degrees C terminals. And finally, the last section in 110.14 talks about torque, terminal torque. If I don't tighten a wire up tight enough, right, underneath that lug, whatever kind it is, wire bonding screw, standard screw, whatever my lug is, righty, it's going to be loose, and I could get some heating, unwanted heating, And let's see, the high resistance, some more heat, loose wire causes high resistance, causes more heat, on and on it goes. Once again, I could end up with a fire in my hand. Terminal screws are going to vibrate, a little bit, right? 60 cycle hum, I suppose, like on a transformer, certainly. Also, as current passes through the wire in the terminal screw, the metal heats up and cools down. They're different sizes. They expand and contract at a little bit different rates. And so wires tend to work themselves loose under terminal screws. So parting of the listing and labeling of all of this equipment is that the manufacturer comes up with that optimal torque that we should apply to those terminal screws. So when the manufacturer supplies that torque value, we have to pay attention to it. That's what we have to follow, okay? And then we have to use some type of approved torquing means to do that. So we can use torque screwdrivers, torque wrenches, whatever is applicable. But there are other things as well. We can use breakaway bolts, shear bolts, in other words. Well, they've got 2 heads on them. And so we tighten it down using the top head. And when that shears off, bingo, we hit the right torque value. We still got a head there, so someday we can take and loosen that bolt and pull it out if we need to. So anyway, that is 110.14 in a nutshell. Oh, by the way, the informative annex in the back, which one is it? Informative annex I gives you torque values as well. Also, the NFPA 70B, which the code book references as a recommended practice. That's not true anymore. The NFPA 70B is now the standard for electrical equipment maintenance. And in section 7.2 of 70B, it has information on torquing on it and how, different ways that we can check torque requirements. All righty. So anyway, that's it for 110.14 electrical connections. Once again, we thank you for attending today. Hope you got a little bit out of it or some good review for you, whatever the case may be. And remember, this is brought to you by EC&M Magazine at ecmweb.com. They're part of the portfolio of Endeavor business publications. So Make sure you sign up for this premium content. We'll see you next time. And between now and then, work safe.